This podcast is on solubility equilibria. In the 8th edition of Zumdahl, it's chapter 16. In the 7th and previous editions, it's the second half of chapter number 15, but regardless, the material is the same. And what it deals with is the equilibrium that is established with slightly soluble salts. In a previous chemistry course, you may have learned that silver chloride is insoluble, but in fact it is slightly soluble, and that solubility is easily described because it's an equilibrium. It's an equilibrium of a special nature, and so we have a K value called the Ksp, known as the solubility product constant. It is an equilibrium constant, so what you will notice from the next three that appear is that it is the same as if you were doing equilibrium, where the concentrations are raised to the respective powers. Now, this is useful because it enables us to determine whether or not a precipitate might form in an aqueous solution of one of these slightly soluble ionic solids. We calculate what's known as an ion product, or Q, and you calculate it by substituting into the Ksp expression the concentration values that you have for the various ions. If that Q value calculates to be less than the Ksp, the solution is unsaturated and no precipitate would form. If they are equal, the solution is saturated. And if you get a Q value that is greater than the Ksp, you might form a supersaturated solution, but more commonly, a precipitate will be seen. Now, from the 7th edition, we have this table of Ksp values, and you'll notice there's quite a number of them. And it, in some way, matches the solubility rules that you might have already learned. Notice that the carbonates and the hydroxides and the sulfides are mostly insoluble. Those tables will be available whenever you need them. It's two definitions. Molar solubility is the concentration in moles per liter, and solubility is the concentration at solubility in grams per liter. And so we need to make sure that we can distinguish between them. The graphics at the bottom show the difference and the way of calculating it. So you start out with the solubility of the compound in grams per liter, convert to concentrations, get the Ksp, and then you can get the molar solubility. And I have an example, although it is not exactly like this, that follows. What is the solubility of silver chloride in water in grams per liter? Well, we have the equilibrium expression for the dissociation of the ions as it dissolves, and we look the Ksp up in the table. We then set up our ice chart like normal. The initial concentrations of silver and chloride ions is 0. The change will be plus x. At equilibrium, they'll both be x. The Ksp expression is Ag plus times Cl minus. It's x times x, or x squared. X therefore equals the square root of the Ksp, which happens to be 1.3 times 10 to the minus 5. What that means is that the concentration of the silver ion and the chloride ion is both 1.3 times 10 to the minus 5 molar. So in a liter, we will have 1.3 times 10 to the minus 5 moles of silver chloride that actually dissolved. And so then we multiply that by the molar mass, cancel the units, and we get 1.9 times 10 to the minus 3 grams per liter. And so you would report the solubility of silver chloride as 1.9 times 10 to the minus 3 grams per liter. Now, here's a little wrinkle. What is the solubility of lead 2 fluoride in 0.01 molar lead nitrate? So you'll notice that the lead ion is common to both, and indeed we call this the common ion effect. The solution to this is very, very similar to what you may have done in equilibrium. You need the equilibrium expression and you need the Ksp value. Okay? The initial concentration of lead now is not 0, but it's 0.01. Chloride's still 0. It's still plus x. It's plus 2x now because you've got two F minuses formed. At equilibrium, we have 1 plus x. We have 2x. The Ksp value is the lead 2 plus times the fluoride ion concentration squared. And so we end up with Ksp equals x plus 0.01 times 2x quantity squared. And we're saying, ooh, I don't want a quadratic equation, or in fact a cubic equation. So we make an assumption. We're talking about relatively low solubility salts. So let's assume that the amount that dissolves, okay, is in fact so small that x plus 0.01 is basically 0.01. Run through and solve. X is equal to the Ksp divided by 0.01 times 4 is 1 times 10 to the minus 5. And indeed, 1 times 10 to the minus 5 is a lot smaller than 1 times 10 to the minus 2, so our assumption is valid. The lead concentration would be 1 times 10 to the minus 5. The fluoride is 2 times 10 to the minus 5. And so the solubility calculation is the same as before, and we find that we have 2.5 10 to the minus 4 grams per liter as our final answer. The common ion effect usually involves using this assumption, and this assumption is 99% valid. We certainly would not ask for a cubic equation to be solved in an AP chemistry class. It's not a math class, it's a chem class. Well, as I said earlier, you can use this to determine whether or not a precipitate will form. So what if 2 mils of 0.2 molar sodium hydroxide are added to a liter of 0.1 molar calcium chloride? Will we get a precipitate? The ions that will be present in the solution are sodium hydroxide, calcium, and chloride. The only possible precipitate is calcium hydroxide. In fact, it's the only one that has a Ksp value out of sodium chloride and calcium hydroxide. Is Q greater than the Ksp for calcium hydroxide? That's what you need to calculate. So the concentration of the calcium ions is 0.1. Okay. Now, the volume increased. In the case of hydroxide, we need to calculate concentration, and it still is about 4 times 10 to the minus 4. This particular problem is set up so that the volume change going from 1 liter to 1.02 liter is actually not very significant. If you were adding volumes that were significant, you would have to do this calculation for both of them. But here again, we're making an assumption. The Q, or ion product, is equal to 1.6 times 10 to the minus 8. You go to the table and look it up, and you determine that the Ksp for calcium hydroxide is 8 times 10 to the minus 6. 1.6 times 10 to the minus 8 is less than 8 times 10 to the minus 6, so the Q is less than the Ksp, and no precipitate will form. That's the analysis that you would do for this kind of question. Now, Ksps, in fact, are very useful, because qualitative analysis of cations is based on Ksp values. And this is a typical qualitative analysis scheme, or qual scheme, where you add reagents sequentially, and based on whether or not something precipitates, you can actually identify an ion.